So again, my name is Ron. I'm a software engineer in StarTree for the last 2.5 years. The main focus for the last probably 2 years for my work here is to focusing on the multi-stage engine, which basically enable the query time join in real time for real-time data for Apache Pinot. So here, pretty much what I'm gonna introduce a little bit about Apache Pinot for folks who doesn't too familiar with how Apache Pinot works. I'm going to deep dive into a little bit about the join semantics and some of the traditional general join introductions. And then I will dive specifically into how Pinot implements real-time join. And then afterwards, I'm going to talk a little bit about the bits and tricks regarding how to make it performant, efficient in your production environment. Okay, let's get started. So, for folks who is not familiar with Apache Pinot sits in the OLAP data store stack, which is basically located here on the bottom right corner. So OLAP databases are basically kind of like analytical driven databases. They typically don't have transactional database guarantees. They don't have strong consistency guarantees, but they are extremely efficient in terms of like retrieval of data, making analytic results, etc., etc. So those are the things that we are mainly focusing on in terms of analytical workloads. They are very efficient in terms of user-facing analytics, as well as some of the internal-facing analytics as well. So the idea for OLAP databases to coexist with their lakes, their warehouses, and some of the transactional databases is serve as kind of like a one-stop shop for doing all sorts of like low latency, high throughput analytical workloads. It has been exists for many of the like larger companies that I work with, and then also it's a super um, energy efficient, I would say, or like computationally efficient way to manage these type of data and use cases in real time. Um, so what exactly is Apache Pinot stands out in the analytical world? So some of the key differentiators here is it's basically just like a pure columnar databases. All of the it's stored in columnar format. A whole bunch of indexing mechanisms are basically there to basically pre-compute many of our computations like predicates, aggregations, etc., etc. So these are the pluggable indexing mechanism or frameworks that basically make Pinot extremely good at pre-computing some of the components. We do also support real-time ingestion. As you can see previously, we do support ETL or real-time ingestions from Kafka, Kinesis, or PubSub, or some other real-time basically PubSub systems. And these type of capability are basically making sure that Pinot can actually query data that is just ingested like milliseconds ago. Also, it's highly scalable and fault tolerant. Pinot can be scaling up to, I think, like, I'm not exactly sure how many of our customers are actually doing that, but many of the OSS customers can scale up to thousands, if not tens of thousands of machines easily with like horizontally scalable performance so that the more nodes that you actually put into the system, the better the performance and the higher the throughput. Here is kind of like a brief overview regarding how Apache Pinot works as kind of like a component, a diagram. So on top of that, we have a control plane. So the control plane is basically serve kind of like a metadata manager for the entire cluster of Pinot. It uses Zookeeper is actually the data store for the metadata, and we also use Apache Helix, which is basically wrap around our controller to control the tenants and participants of this entire cluster. So if there is a server goes down, server comes up, it will basically managing via Apache Helix. On top of that, we have two types of like components, or three types of components specifically. One is the broker, which is a stateless machines that basically perform the computations for the queries, dispatch them to the actual servers, which is basically the machines that host the data. And of course, servers actually is participant into real-time servers and offline servers. And the real-time servers are basically serving the ingestions from Kafka, Kinesis, to some other like puzzle systems. The offline server is usually hosting some of the more batch ingested type of like data. We do have a auto-scalable minion mechanism that basically trying to compute some of the transformations or aggregations or some of the compactions for example, like if you want to ingest CSV data from an S3 data sources, we basically use minions to transform them into kind of like the columnar format in order to ingest them into offline servers for it to be served out for query time use cases. Any questions on Apache Pinot, or can I just jump forward? Okay,
Uh,
so
so,
go ahead.
when you say real-time servers, all these are hosted on-prem or they are on cloud? And uh, does it mean that these are storage servers with less compute on them, or what's the configuration?
That's a good question. So the real-time servers and offline servers are not actually physically separated machines. A specific single container can be configured to both serve the real-time role as well as the offline role. So it doesn't actually separate them physically. And each one of these machines are basically containerized like components that you can actually scale up and down, regardless whether you're doing it on-prem or you're doing it on the cloud. As long as you kind of like, hey, have a container concept, you can basically deploy it.
So by
Well,
container,
obviously it had. Sorry, go ahead.
by container in Docker container, right?
Yes,
Those.
yes.
So basically, it is taking care of the compute. And where is the storage coming or getting attached to this container? Is it coming from cloud or some volumes? Like how?
Um, Generally speaking, it's managed by the Docker containerization. So, for example, if you're let's assuming that you're using AWS machines with kind of like an EBS attached storage, right? So that storage is viewed as kind of like a local file system to the container itself, even though it's actually accessing a remote storage. That is not something that Pinot differentiates. It basically just utilize whatever local storage that is configured to the container to be used. So you can configure to use local SSD or you can configure to use EBS attached storage. That doesn't make too much difference there.
Okay, cool. Thank you.
Okay. Mhm. Good question though, yeah. Any other questions? All right, so let's jump a little bit ahead into the spectrum of joins, right? So I think majority of data engineers or data analytics users, they will know that the spectrum of joins are basically scattered into several of these examples. For some reason, I think I missed one slot. Um, Anyway, so basically there are several ways to do joins, right? So you can there are a couple of different types of joins. Obviously, there's kind of like left join, right joins, lateral joins, or some of the more complex ones, like a self-saving joins, decorrelation joins, etc., etc. But all of these join algorithms or join types fits into the relational algebra for basically like correlating two tables together. So there are a lot of ways to do these type of things by correlating one table with another table in the OLAP databases. I categorize these things into four different categories. One is called star schema, right? So basically you have one join key from one fact table. You have a whole bunch of dimension tables that you want to basically correlate them. For example, you have a transactional data table, and they have kind of like a dimension data table for, let's say, some of the entities like user, like merchants or items, etc., etc. Right? So you have these type of like property or dimension value tables, but at the same time you have like ever-growing transactional tables that you want to basically correlate them, doing some aggregations, doing some filtering, etc., etc. So star schema is basically fitting into this category. You are basically maintaining all the table in their raw format. You don't actually do anything during the ingestion. The join actually happens in real time in query, during query. So there are no pre-computations. Everything is being done on real time. Obviously, it's extremely easy to manage it in ingestion time. It will be relatively hard to scale that out during query time because of the computation is quite expensive. Um, so one step further is denormalization, right? So you can actually pre-join the tables to avoid these type of expensive query time joins. For example, you have a transactional table, you have item tables, merchant tables, and user tables. You can basically create kind of like a pre-join tables, transaction and item, transaction and users, and transaction and the merchants. Then you have three denormalized tables, and then they can basically serve out the query time join and they can serve out the query-time join results by directly looking at the pre-join results in their ingestion time table. So it's going to save a lot of time during query, but it's going to make the ingestion mechanism a little bit more expensive because you have to actually look up the join results at the time when you ingest the row of the data for your transactional database, transactional table, sorry. Step one step ahead is you want to also pre-aggregate some of these data. For example, like the join that you do between your transactional table as well as your merchant table is to basically pre-aggregate all of the total counts for every single merchants for every single day. Then you can actually pre-aggregate these results into kind of like an even smaller table. And then you know that these type of use cases are going to be served out quite well because these type of like pre-aggregation is going to be performed a lot during your query time. Then this pre-aggregation is going to save even more computation. So one more step ahead is the pre-cubing. So basically, you can actually do this via multiple different dimensions, via multiple different angles to basically kind of like a push aggregate on one of the dimensions or multiple one of these dimensions in order to get some of these pre-aggregation results in various different fashions. So from the left to the right, the aggregation or kind of like the pre-computation gets even more and more expensive, but at the same time, the query time computational complexity gets less and less. So normally speaking, most of our OLAPs databases out there is doing one of the three in the right corner, denormalization, pre-aggregation, or pre-queue, so that you don't actually have to do the join during query runtime. For the scar schema mechanisms, Apache Pinot historically prior to 1.0 release was related on relying on the external query federation systems to do these type of joins. For example, we have a Presto Pinot connectors, a Trino Pinot connector to basically ship or shipper some of these data that has been like ingested into Pinot into Presto or Trino in order to do the joins via the star schema mechanism. So obviously you have the drawback here is you have to maintain a separate system outside of Pinot. We have to maintain the connector and making sure that everything works fine. Also at the same time, you need to basically like allocate resources for the federation system as well as the Apache Pinot itself. So it's very complex. It's really hard in terms of operations. It's just kind of like extremely expensive in order for maintenance. So let's go back to some of the use cases that we wanted to touch bases on these type of joins, right? So like I said before, you have denormalizations, the dimension joins, or you can basically distribute your dimensions, or you can actually do your native joins. So the spectrum of the join and the ETL mechanisms, again, like I said, becomes in this case it becomes more and more expensive for the query time towards the right and more expensive during ingest time towards the left. So I'm going to re-show this use cases once we have more questions regarding the use cases afterwards. But let's jump a little bit ahead into this graph. So basically, as we measure some of our use cases prior to the 1.0 release, especially when we partner with Presto Pinot connectors, we realize that the star schema use cases are the most flexible ones because it does not require our customers to rejoin anything to do any pre-computations during ingestion. And it's just basically the most flexible way to deal with that data. But at the same time, it's also the most expensive and the longest in terms of latency and the lowest in terms of throughput. So this is what we are trying to fix. We are trying to get somewhere in between to basically do this type of algorithms in Apache Pinot. We wanted to achieve the same level of user-facing analytic flexibility so that the user doesn't have to worry about how they actually ingest the data. But at the same time, we want to provide an order of magnitude better performance for these type of use cases in Apache Pinot native. So as you can imagine, the benefit for this is extremely high. You potentially can get rid of one external system. At the same time, you're actually gaining order of magnitude in terms of performance. So here comes the multi-stage engine. So as I kept mentioned a little bit before is before 1.0, we are mainly on the real-time, low latency, high throughput use cases, but we are a little bit behind in terms of the QB flexibility. And this is what we are trying to tackle for the 1.0 release with the multi-stage engine, especially for the joint use cases. So one thing that I just mentioned here is we wanted to basically be able to eliminate the query federation systems entirely in order to support these type of star schema use cases. With this multi-stage engine, we will be able to do star schema joins, denormalizations, or pre-aggregation or pre-queue and much more. We have supports for window functions contributed by LinkedIn. We have a whole bunch of things, other type of like optimizations contributed by Uber and some other folks in the community. So this entire engine is extremely exceptional in terms of performance for these type of use cases. So going back to the actual architecture design on what exactly is changed comparing to prior to 1.0. So before 1.0, the query engine is basically running a single map reduce. So the broker receives the query gets compiled into a whole bunch of single machine computational plan. These plans are basically executed in the real time and the offline servers, depending on where the data actually locates. And then each one of these servers sends data back to the broker, and the broker basically just doing the final sanitizations, reduce the results into the proper format, and then return it back to the user. As you can imagine, there are several problems here. The most important problem here is broker becomes a bottleneck when data is extremely large. But at the same time, if you want to do joins, then your broker becomes the only location that it can actually do the join, which is a single machine that does not actually horizontally scale. So what we ended up designing is, why not make like some intermediate steps that you can arbitrarily chain in order to do these type of computations distributed. So what we actually ended up developing is a data exchange layer that basically can shuffle data around between the servers of Pinot. And then at the same time, what we can actually do here is chain arbitrary number of these intermediate computational stages. So you can do full SQL semantic joins. You can like use some of the joins that basically can run up to like 10, 20, or even 30 type of these type of joins. And then some of these computations can be kind of like relocate or reuse some of the temporary tables, view tables, etc., etc. So there's basically after the executional model change, there's no limit on what type of queries that can run on Pinot. Okay, so any questions so far before I go into the user-facing join query analysis? Okay, so let me go into a little bit of the join query. Right? I think this is the more interesting part that a lot of the users will be able to see the benefit for this. So let's use a very typical join query example, right? So we have two tables. They are both indexed by ID, for example, like some of the transactional IDs or kind of like custom IDs, stuff like that. So what we want to do here is I wanted to figure out how many models from the first table and has a row count that comes with join results correctly match from the other table, right? So for example, like this is an inner join or a left join that basically matches the IDs and trying to come up with kind of like some of the organizational results. So it's kind of like a typical star schema joins, right? So you're trying to enrich the fact table with the dimension table to basically doing some filters on the dimensions. So for these type of joins, you are not able to do this. Well, we can actually do this with just the single stage prior to 1.0 model, but the entire join needs to happen in broker, which is kind of like a single one, a failure, it does not scale. So what we can actually do here is, by definition, it can actually automatically run in the V2 engine or the multi-stage engine. It does not do any optimizations or any rewrites for the query. The query basically execute as is. Now, why do we wanted to say that this is actually an extremely efficient optimization, or this is actually a very fast or order of magnitude faster star schema use cases compared to a federated system? Is that we can leverage a lot of the things natively available in Apache Pinot in order to optimize the join speed. One of them is called reduce operator overhead, right? So some of the operations that we can actually push down to the computations closer to the servers that host the data, the better. For the query federated layer, we will most likely not able to do some of these optimizations, but in terms of the native join executional model, we can push down a lot of these things. For example, we can actually do the filters before the join. We can actually do some of the pre-group buys on the joins, etc., etc. These are things that are actually more efficient. And the other type of this is minimizing data shuffle, right? We can actually strategically place the two tables in a way so that they are minimized in terms of data movement. For example, in this case, if the data are distributed according to the ID column, then most of our joins can happen either in like locally, or it actually happens in kind of like without too much of a data shuffle. We can get into this in a little bit. Last but not least is it can leverage some of the pre-computation of Apache Pinot's power natively instead of actually having to deal with this without the index on the external federated system. So one of the examples that I wanted to mention here is leveraging the index, right? So for example, I can basically rewrite the query in this way. You don't actually have to rewrite it, but like intuitively, this is actually what happens behind the scene within the Apache Pinot native join engine. What happens is it will basically apply the organizational ID filter first before you actually perform the join, so that the join results are actually performed on top of an index lookup instead of a table scan, and then using the filter to basically get rid of the things that are not matching the organizational ID. So in this case, the inverted index is going to be used to basically look up only the subset of the rows within table 1, and those results are going to be shipped over to the to table 2 before the join. So this most of these optimizations are going to be automatically faster compared to just doing a native join. Another example is reducing the data shuffling. We can leveraging the StarTree index, which is basically a pre-cubing, in order to like speed up the count star. What we're actually doing here is because the join is happening against the ID column, and subsequently is trying to actually doing the start count of the row on the T1.model column. That means any number of rows that we actually computed prior to the join, grouping by the model and the ID. In this case, it should be ID and model. I think there's a typo here. What happens is if you grouping by the ID and the model and basically doing the pre-count prior to the join, what actually happened here is you can actually do the summing on top of the pre-count results and then basically achieve the row count. Let's say the model and the ID column are low cardinality in their combination. And this will basically reduce extremely automatically less data to basically be able to shuffle around to do the join. Next is data locality, right? So this is basically echoing back to how these type of data exchanges are being computation, right? So basically what these data exchanges trying to do is shuffle the join by their join keys to the servers that is basically co-located. So for example, if you have a join key of 1, 2, 3, 4, 5, 6, 7, etc., and you have 3 servers to do the join, for example, like 1 and 4 is going to shuffle to the first server, 2 and 5 is going to go to the second server, 3 and 6 are going to the third server, right? But if your data is already pre-partitioned, there are a lot of optimization we can do. So this is kind of like the naive solution. As you can see, the data transfer, the dotted lines are basically just everywhere. Majority of the data is being shuffled across the wire to a different set of servers. But if you are already pre-partitioned by your, let's say your fact table is already pre-partitioned by the ID column, then the only thing that you need to shuffle here is your dimension table, which is basically the smaller one that needs to be matching the partition of your right table, which left table, which is the fact table. To step one step ahead is if both your table are partitioned by the same ID, then all of the join can be happening locally within each one of these servers. So you don't actually have to pay any data transfer costs in order to get these joins correctly computed, which is a huge benefit, considering that most of the time for the latency is governing by the slowest connections in the data transfer step. Now coming back to some of the algorithms that we use to basically do this, right? So as you can imagine, there are several ways to shuffle the data. The first way that you want to do is, even if the data is not partitioned by the left table, if you are broadcasting the right table to the specific location of your left table, you can actually do this. This is actually one of the use cases that we do for the broadcast join for factin, that you don't actually have to do a lot of computations or data shuffling just by pushing one table to another table from their servers. Obviously, the naive solution is basically doing a shuffle hash join, which you basically redistribute both the left and the right table to a specific set of tables afterwards. And the third type is you can basically doing a direct lookup. So this usually means that your right table is kind of like a primary key index location, and those rows are basically just a single match. So instead of doing a join, what you're actually trying to do here, you're guaranteed that your right table only have at least most one row matching the left table, and what you're actually doing here is just doing a dimension lookup. So there's no join involved. There's no hash key or hash table needs to be created. The reason why I mentioned this is because these three types of joins are actually controllable by query planning. So at this stage, because the planning phase is relatively expensive, we don't actually run these type of optimizations by looking at the table statistics. We are actually relying on the users who has more knowledge regarding how the table sizes are being allocated in order to do these type of things. For example, if we want to use the broadcast join, right, sorry, the broadcast join algorithm, in this case, instead of the shuffle join, which is the default, what you can do is basically tell the system that I wanted to do this as a dynamic broadcast join, which is basically suggesting that the left table is order of magnitude larger than the right table. And then the algorithm is going to be extremely fast in terms of the actual data transfer because you're actually not doing the transfer both tables, shuffling them and send them to the intermediate stage. You're actually trying to shuffle the right table into the left table in order to do it. Some of the other things that I mentioned here is not actually a full set, but a lot of these things you can actually look it up in the Pinot official doc. Is like, for example, you can actually say that the data is already pre-partitioned by the group by key. What you can actually do here is skip the actual computations for some of the more expensive operations and directly get to the final result. So some is probably a little bit more nuanced example. Let's say this is a count distinct. So in order to do a distinct count for a specific group, you actually have to compute the actual distinct values for this specific like columns. But if you know that every single one of your group keys are going to be located within a single server, you don't actually have to shuffle the entire list of items in your column. You can actually just return a count. Any questions so far? Okay. Okay, so what's the catch? It seems like this is an extremely efficient, very smart algorithm or engine, but there are a lot of caveats. As I can imagine, some of you guys might have wondering in your head right now is, this is designed to replace the query federated system when you're doing a star schema type of join. It's not designed to do ETL-like joins, right? So for example, like one of the things that you don't want to do here is to write a 3,000 line of like ETL-like queries to run, like the design to run in Presto or BigQuery or some of these like more expensive engines. These engines can host queries that run in terms of minutes, in terms of hours, in terms of days. They are designed for fault tolerance. They're designing for distributed data shuffling, spill to disk, everything like that. But the multi-stage engine that we design here is purely in memory. The entire system is designed for streaming fashion so that the entire algorithm should be finishing within a second to sub-second latency. If anything goes beyond that, and then one of the component fails, the entire computation needs to be restarted. It's kind of like a trade-off that you have to make because the coordinator or the controller mechanism that basically coordinate all of these distributed computational tasks is more expensive in terms of latency when you are driven towards a sub-second domain versus you actually have to maintain the fault tolerance, right? So recomputing the entire plan in a sub-second latency use cases is more efficient comparing to actually have to track the entire executional diagram, figure out which one is failing, and then coming back with kind of like a delay reschedule mechanism. So that's the trade-off that we make. So it's not Presto, it's not the BigQuery, it is not designed to replace all of these cases. It's specifically designed for second to sub-second latency join queries. So some of these use cases that I basically said is star schema aggregations, customer 360 enrichment, and some of the other use cases that basically is sort of like warrants a user to do one or two levels of joins with more, probably like one or two fact tables tops. Another thing I wanted to call out here is it's not designed to be resource efficient compared to some of the distributed systems. The multi-stage engine is a pure in-memory system that all of the operations or all of the tasks are basically executed at the time of the execution of the query gets reached to the broker. So everything is scheduled all at once. Everything is starting to grab their memories all at once, and everything is running in the streaming fashion all at once. It's designed to minimize the latency as much as possible. some of the task that is scheduled all at once is going to wait until the previous task to start producing this first data in order to be efficient. But there's no coordinations in this case, so the latency is minimized. But some of the resources may be idle, but it's actually taking up the resources of the computational cluster. So, like I said before, some of the comparisons with some of the Faraday systems is you are doing with Presto Pinot connector, you're doing some of the limited filter and aggregation pushdown, and that's it. But the majority of the computational joins are actually happening in the Presto Training workers, and these are the things that you do in a traditional like pure Faraday system fashion. But what you can do with the multi-stage engine is we can aggressively push down all of the things that we can do to leverage all possible indexes. Works with other Pinot optimizations such as pre-cubing and pre-aggregations. And then we leverage the data locality that users actually predetermine but when they ingest the data in order to lower the network latency. And we have extremely simple architectures, right? So everything is running at the same time. There's no coordinators. All of the nodes here, it's basically just like virtual nodes. You can actually run these servers, the offline servers, real-time server, intermediate servers, all in the same container. There's no limitations on that. And then what's the more important is the broker no longer becomes a bottleneck. It's order of magnitude better in terms of throughput and latency. So here is one of the examples that I think we benchmark for one of the data sets that we previously do is if you don't use just naive hash joins, the latency goes beyond 120 seconds. You're shuffling like billions or tens of billions of rows across the wire. If you optimize the joins, optimize their layout, doing the aggregational pushdown or the pre-aggregations, if you're doing the pre-partition or web computation by, co-locate the tables together within the same servers, ultimately what you can actually do is reduce the data shuffle from 68 billion to 2 million rows, and your latency comes down from 120 seconds to just like 0.5 seconds. So this is how the performance measurements that you can actually do, right? So the naive join is basically what you actually can like theoretically achieve in a generalization mechanisms by using kind of an external shuffling or federated system. And here's what you can actually do by boosting more than 200 times the performance using the native joint Pinot engine. I think that's the entire presentation today. Any questions?
Hey, Rong, I have a couple of questions. On that last slide with the list of optimizations, you mentioned that um, how the data is placed on the servers is important to the performance, right? To be able to leverage some of these optimizations,
Correct.
like locating table data on the same servers is one example that you provided. Are there any other examples or recommendations in terms of placing the data or optimal, like providing hints to the queries to achieve better performance? Like,
Yes. So there's two questions that needs to be answered here, right? The first question is how do you actually lay out the data so that it's optimized for a specific type of queries? Generally speaking, it won't be efficient to everything. It's specifically optimized for one type of queries. And the second question is how do you utilize the table index hints in order to do this more efficiently? So let me go back to this diagram, right? So the data locality is trying to solve the majority of the problem on the data transfer layer. So the goal here is to transfer as minimum number of rows as possible across the wire so that you can actually achieve better throughput, right? Because if you know that the data that you're shuffling out of your table scan stage is going to be dropped or going to be compacted afterwards, there's no reason to shuffle multiple rows out of your table scan stage. Instead, you can actually do that pre, like, like predeterminedly. So one example is this is if your table is already pre-partitioned, then, for example, if you have the join key pre-partition, like into like, let's say 0, 1, 2, or 3, or like 4, in this case, 4 partitions, then what you can actually do during the join mechanism is you can actually shuffle the your right table, which is unpartitioned, based on your left table's partition key. So in this case, let's say your partition key and partition function of your left table is say member2, right? So a very common hash function. What you can do is basically using the exact same hash function to compute for each one of the rows that you're actually going to shuffle out on your right table, which is the blue one. And then you can predetermine exactly where the set of server that you need to shuffle or ship this data to. So that in this case, it's going to save your entire left table shuffle across the wire. So this is extremely useful if you're doing a fact-dim join, where your green table is much larger than your blue table. Another example is if you're doing a fact join, right? So both of these tables are ever-growing large fact tables. Then what you can actually do here is pre-partition both of these tables by their join key. So majority of our use cases in Star Schema and Customer 360s, you are actually doing this via, let's say, customer ID or transaction ID, etc., etc. So most of the case when you're actually trying to join these type of use cases, you pre-know that exactly what is the most used join keys that you're actually going to do. So by that definition, you can actually pre-allocate the exact same set of servers to host these two tables. With that in mind, is your join stage can happen locally. You don't actually have to shuffle in data across the line. That being said, some of the scar schema enrichment, for example, if a transaction table, you have kind of like a customer database, a customer table, you have a merchant table, or you have an item table, which is an order of magnitude smaller. It does not make sense for you to collocate both of these tables because your transaction table will have customer ID, merchant ID, and item ID, right? So you have a transaction ID, which is your primary key, but none of these join keys are actually your primary key for your left table. Then what you actually do here is you can actually broadcast your right table to your left table, because even though your left table is not partitioned, because your right table is small, if you replicate your right table to all your left table, then you can still do every single one of your joins locally without actually need to worry about whether the join key is actually entirely covered within your specific server. So distributedly, you can actually say that by applying the broadcast join, because you know that the right table is much smaller than your left table. So this is where the hint comes from. So the hint is basically telling you you are going to pick one of these three type of join algorithms to use, but it's largely depending on how your data is located and what exactly is the data pattern that you're actually looking for. Does that answer your question?
Yes, thank
Okay.
you. Pre or partitioning based off of the join key makes a lot of sense.
Well, it's partitioning based on the majority of your deterministic use cases, right? So if the use cases that you want to do in an ad hoc fashion that falls out of your join key, or it's kind of like the type of use cases that you're trying to do is not the one that you partition, then you need to pick the other way around, right? So for example, the lookup join is a pretty useful example, right? So let's say you want to join the transactional table with a customer dimension table on that customer ID. The customer ID is actually your primary key for your customer table because there's only one row guaranteed maximum for each one of your customer IDs. You may have a customer ID in your transaction table or the left table that is not there yet because your ingestion delay or something like that, but it's guaranteed that no more than one record is going to be exist on your right table. That automatically guarantee that when you're doing a join in that fashion, at most one row will be joined successfully between your left table and right table. So you can actually not build any dimension or hash maps, or doesn't need to be worrying about how the final join result is going to explode beyond your left table size, right? So the size is pretty much manageable. You're actually going to do at most one row lookup, and that's it. So you can actually optimize that in that fashion. Okay. Any other
Yeah,
questions?
I have one question, if you don't mind, Ron. Can you
Uh,
go to the diagram where you have the nodes kind of laid out between intermediate and
oh,
yeah,
this one?
yeah, that one, yep. So in the middle there, where it says intermediate compute store stage, are the intermediary servers, are those dedicated servers to only be intermediary, or can they also be real-time and offline servers?
Yeah, it can be anything. So these are basically just think about these as an individual service that is able to be turned on and off on each one of the Docker containers that you launch in the cluster. So it doesn't really matter where you host these servers. That being said, is for every single offline real-time service, they also run an intermediary server by default. So you can actually run the entire engine locally within one pod or one container.
I see. Thank you.
All right, I think that's all for today. If you have any more questions, feel free to reach me in the Apache Pinot Slacks or the StarTree Slacks, community Slacks.